Hello, everyone. All right, we are doing chapter 2.8 today. And let me just get myself set up here. Here we go. All right. Anyway, the book that we are doing is in the video description. So get the book. It's a really good book. The download, it's free because this is part of the Creative Commons. I have a physical copy. It's very nice. I am telling you this for your own benefit. I don't get any kind of benefits from people downloading the book, but it's a beautiful book. So, yeah, get the book. And you can follow along, and you could also look at the answers in the back so you'll know if I'm getting it right or wrong before I do. Now, remember, usual rules apply. I am doing this as a study stream. This is a class that I did not pass. I've taken it twice before. Both times I dropped it for the sake of focusing on work. I am a professional landscaper and handyman, and I'm a figure skating coach. I am not a mathematician, but I am working on a double Bachelor of Computer Science and Pure Math. All right, so let's do this. I also really enjoy math. Okay, not that I'm any good at it, but, I still enjoy it. Okay, so I'm going to read through chapter 2.8 just so you know ahead of time. There are no questions to be answered in this, so we'll just kind of work on the examples. So this, we're going to see if we can power through. Let's see how far we get tonight. All right. (2.8) More on conditional statements. It is time to address a very important point about conditional statements that contain variables. To motivate this, let's return to the following example concerning integers. All right, I'm just going to write the example. X is a multiple of 6, which implies X is even. Now, if you think about it, this is a true statement. When we say that X is a multiple of 6, what do we mean? That means that that means X is divisible by 6. So if we take X divided by 6, will result in some kind of whole number. We'll just say integer. Okay, it'll contain the integer sets. So if X is a multiple of 6, well, that's just my own thing that I wrote there, but essentially it's what I'm trying to utilize more of the math language. So X is a multiple of 6, which implies that X is even. Except in this case, this multiple of 6 means that X will result in a whole number. Now, is it true that X is even though? If it's a multiple of 6? Well, we know that 6 is even, and if X divided by 6 results in a whole number, therefore then X would have to be even. Yeah, so that's a true statement. Anyway, that's just my own analysis here. Reading on. As noted earlier, since every multiple of 6 is even, this is a true statement. No matter what the integer x is, we could even underscore the fact by writing the true statement as follows. I'll take out what I wrote here. So this is our universal quantifier. It means all x containing integers or all x which are members of the integer set, or all x integers. X is a multiple of 6, and that implies X is even. All right, and period. So that's the true statement, and then, yeah. But now switch things around to get the different statement. X is even, which implies X is a multiple of 6. That's true for some. Well, where would it be false, though? Let's think about it. So x, all we know is x is even. Well, what if x is 8? That's not a multiple of 6. So, yeah, that's true in some cases. That's what you would call an open sentence, where true for some but false for others. Okay, I'm reading on. This is true for some values of x, such as -6, 12, 18, etc., but false for others, such as 2 and 4. Thus, we do not have a statement, but rather an open sentence. Recall from section 2.1 that an open sentence is a sentence whose truth value depends on the value of a certain variable or variables. However, by putting in a universal quantifier, we get all x containing integers, comma, x is even, which implies x is a multiple of 6, which is definitely false. So basically, what they did was here, if you flip this around like that, that would become a false statement. And you should be able to understand that. So that means for all x integers, if they're even, they're automatically a multiple of 6. Well, 100 is even. That's not a multiple of 6. So yeah. Or you can think about like 20 is even, is not a multiple of 6. All right. Let's get rid of that. In general, given any two open sentences, P of x and Q of x, about integers x, the expression, okay, all x integers, comma, P of x implies Q of x. So this is P implies Q. So whenever we have an implication, the way I tend to think about it is you have the P is the cause and Q is the effect. But in some cases, now keep in mind when the truth value for it, the truth table, on an implication, if they're both false, the statement's true. You can think of that as being unchallenged. At least that's how I do. And also, if P is false but Q is true, then it would still be a true statement because Q is the effect. We care about the effect, basically. All right. Yeah. Now, continuing on, but let me just double check on the implication table. I'm still learning all this stuff, so I don't want to mislead you. Well, I prefer double checking everything. There we go. Yeah, you can look at the P implies Q truth table on page 44. If P and Q are true, it's a true statement. If P is true, but the effects didn't happen, Q is false, it's a false statement. If the cause didn't happen, if the P didn't happen, but the Q did, it's true. And if both are false, it's true because it's unchallenged. You can think of it that way. Now again, I'm not a math teacher. There's going to be subtle nuances and differences. So where I say things and describe them, like what I'm saying is correct in the sense that it works. But if you were to drill it down, there's probably nuances I'm missing and so forth. Anyway, but it's good enough for getting through this, at least for my case. This is my study stream after all. All right, let's see here. So we have back to where we were. For all of x integers where P implies x is either true or false. So a statement, not an open sentence. So this right here, this is a statement because it has a truth table. And the truth table is like this. All right, so then we have true P implies Q. And then we're going to say true, 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 false, 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 true, true, false, false, true. This is the P implies Q truth table. Okay? And this is what all the stuff I just rambled on about. And yeah, because this has truth values, this is a, in other words, this is not an open sentence. It has a truth value. All right, so here we go. Now, as we come to a very important point in mathematics, whenever P of x and Q of x are open sentences concerning element of x, in some set x, depending on context, an expression of the form P of x implies Q of x is understood to mean the statement all x containing all x elements of the set X, comma, P of X implies Q of X. In other words, if a conditional statement is not explicitly quantified, then there is an implied universal quantifier in front of it. This is done because statements of the form all x members of the set X, P of X implies Q of X are so common in mathematics that we get tired of putting all of X members part of the set of X in front of them. So what are they trying to say here? All right, so when you're dealing with something and then you're dealing with something of a set, and you're gonna generally say, you know, P implies Q, you're saying P implies Q for every member of the set. That's all they're trying to tell you. So like, let's see here. Let me think about this for a minute here. So let's take this example here we have. So X is a multiple of 6, which implies X is even. Now at the top, this is a true statement. Well, here, what that implies is that every member of the set has to be a multiple of 6 for X to be even. So, in other words, this condition would have to hold for all of them. That's all they're saying. They're saying this part right here is implied. If it's not explicitly, if there's not explicit statements that for some versus for all. Like the difference would be like, say, we could say exists X integer of the that X is a multiple of 6, which implies X is even. So that means there's at least one that exists like that. That's all. That's something else. Anyway, getting going into the weeds here, but let's keep rolling along. The following sentence is a true statement, as in true for all of X. If X is a multiple of 6, then X is even. So yeah, again, I just did it for convenience sake because I had it on the screen, but that's literally what the book is. The thing I just rambled about, they're saying the same thing. Likewise, the next sentence is a false statement, as in not true for all of X. If X is even, then X is a multiple of 6. This leads to the following significant interpretation of a conditional statement, which is more general than but consistent with its definition, section 2.3. If P and Q are statements or open sentences, then if P, then Q is a statement. This statement is true if it's impossible for P to be true while Q is false. It is false if there's at least one instance where P is true but Q is false. So, what are they saying here? The statement is true if it's impossible for P to be true while Q is false. So, if P then Q, well, getting back to our truth table here, it's impossible for P to be true while Q is false. Is false. This statement is true if it's impossible. Meaning they're saying this statement impossible for Q. So that's right here. It's true. A fourth line. It's true if it's impossible for P to be true while Q is false. Okay, so this is going to be a true statement, right? This is the implication truth table. And they're saying it's false if there's at least one instance in which P is true but Q is false. It's false if there's at least one instant where P is true and Q is false. That's line 2. So basically what they're saying is that just look at the P implies Q truth table. And a lot of this stuff, it's a little brain melty, as I like to say. This is why you put pen to paper, you do the truth tables, and then you try to work it out. Like if you're trying to roll this around in your head, it's hard. It's very hard to make sense of any of this stuff. It's not something that we tend to deal with on a day-to-day basis, but at least when you write it down and you start looking at the rows of the truth table, and then you can kind of work it out. Anyway, the great thing about math, especially good textbooks like this, is that even if you are on the wrong track, you can't stay on the wrong track for long unless you're just going to be completely in a cul-de-sac. If you just keep pushing through, you're going to work your way out of it because the things that you're doing wrong will be corrected through subsequent. You'll be forced into the right track, so to speak. This thing is very much on the rails, this book, at least so far. Thus, the following are true statements. That's all right. Let's do a few statements here. Okay, the following are true. If X is a member of the real set, then X squared plus 1 is greater than 0. True, very true. Because if you were to square any number, positive or negative, you're going to at least get 0, but you're not going to get anything negative. So, in other words, if it's a member of the real set, not the imaginaries. So if it's a member of the real set, then, for instance, if it's 0, you square it, you're going to get 0. If it's 1, you're going to get 1. If it's negative 1, you're going to get 1. So you're going to result with any negative number. It's like squaring is basically times itself. You can think of it that way. And 2 negatives multiplied makes a positive. So just basic arithmetic here. But so yeah, this is a very true statement. Very straightforward. And the reason why they put the plus 1 is because if you put 0 in here, which gives you 0, so now you have plus 1, which is still greater than 0. Okay, because 1 is greater than 0. And that's the closest you're ever going to get. The lowest possible number in this equation is not a negative number, it's 0. Because, like let's say you could say negative 100, right? You square that. So you're going to get, 10,000? A minute here. 4 zeros, yeah. There we go, 10,000 plus 1 greater than 0. So yeah, so that is very true. Okay. If a function f is differentiable on the reals, then f is continuous. So this is the fundamental theorem of calculus. I'm not going to get into that right here, but when I start doing the calculus book, I just want to get through, probably through chapter 3 before I start adding. Because I have maybe 5 weeks, so I have to take this class again, and I really want to have the vast majority of this thing behind me and done. And because I don't want to start the class. The thing where it was always my failing is that I would get swamped with work, and then obviously when you run your own business, you have to take care of your clients first, your students, your landscaping, handyman clients, all that stuff. That comes first, and you take care of yourself second. So yeah, that's why I would have to drop all that. And I'm not complaining. I mean, believe me, I'm able to charge my rates and maintain my significant client base because of that. So it was a hard choice I made, a ruthlessly hard choice in a sense on myself, but totally worth it. I mean, absolutely made the right choice as far as I'm concerned. Anyway, getting back to where we're at here. These are just false statements. P is a prime number, then P is odd. Okay, if P is a prime number, okay, let's write this one. Let's have a little fun here. If P is a prime, okay, then P is odd. Okay. Prime is any so prime, again, we're not dealing with fractions here. You can say, well, if I was going to say it's not a whole number, then we get in the weeds, but fractions can't be primes. Primes are whole numbers. And so, yeah, the way it's going to be, any whole number is divisible by 1 in itself. If P is a prime number, then P is odd. Well, we just have to find the prime that's even to prove that this is false. And there's only one prime that's even. How cool is that? Moreover, even more interestingly, it's the first prime. So the order of primes 2, 3, 5, 7, 11, 13, 17. As far as I remember precisely at the top of my head. Let's see what comes 17, 19. Yeah, so these are your primes. As you can see, they are divisible only by 1 and itself. And now the reason why there's only one, by the way, it can't be 1. That is a condition also. Okay, because 1 is divisible by itself, but then the way the primes work, it would kind of break it down when it comes to prime factorization. That's just, we're not getting into that right now. But basically, yeah. So what happens here is we have, starts at 2. Now, the reason why we can't have any more even primes is because everything that's even, by definition, is divisible by 2. So basically, yeah, 2 is the only even prime, and it's the first prime. Everything else is odd. Yeah, pretty cool stuff. I mean, I know some of this sounds really weird. Like, you come across things in math when you're like, huh, I wonder if it could work any other way. And, like, for instance, can you have a universe where, I don't know, let's say 1 plus 1 equals 3? I mean, you can probably create a toy, at least on a mathematical toy universe, at least a very simplistic model, where that is the rule of that. But then it just gets into the weeds. What would you even define as that? Like, I guess it's the closest thing I could think of would probably be the Game of Life, where it was a grid. You could look this up. Basically, you had a grid, like a chess grid, and you had rules. For instance, if you had a box, it was by itself on the next turn. If there was nothing around it, it would die. And if it was a box and you had another box next to it, it would reproduce and create a new box. And so that's like 1 plus 1 equals 3. I guess you could think of it that way. And then there was another rule. If there were, like this, I believe, or too many boxes, then they would die in the next turn. I forget the actual full rules of life, but you could see these really cool models and I guess iterations where they cycle through, where it seems almost like alive. You have things crawling and so forth on a 2D, like a chessboard basically. But it's pretty neat stuff. Anyway, I'll tell you who did it real quick. Let me just look up the name behind the Game of Life. All right, the Game of Life. John Conway did it. So yeah, if you want to look it up. Right. And it looks almost like Space Invaders. You could think of it that way. Again, I'm way getting off topic here. But yeah, I like numbers. I like dealing with this stuff and considering the intricacies. Since we don't have any questions to answer, I'm taking a little longer than usual here. All right. Okay, so we answer that. If f is a rational function, then f has an asymptote. So this is going to be a calculus thing also. Asymptotes basically, hang on a minute. You can think of asymptotes are lines where the function can never get to them, where it gets increasingly closer as it approaches infinity, but it can never cross the line. It never will. It will get infinitesimally close, but never will, for example. Yeah, so that's what an asymptote is. Anyway, that line that exists there, basically, you could think of as an asymptote. But anyway, that we'll deal with all that later. Okay, and here we go. Right. All right, well, that pretty much wraps up 2.8. Yeah, I know it's kind of weird, but yeah, there are nothing to do here. There's a bit of a lecture here, I guess. We have 2.9, translating English to symbolic logic. Okay, this is going to be interesting. All right. Yeah. All right. Wow. The next page is 2.9 is also pretty short, although the translating part might be a little hard, the questions. So I'm going to stop the stream and start that up. And then once we get through that, let's see what 2.10 takes us. 2.10 has questions, and it's pretty long. I don't know if I'll get to 2.10 tonight, but 2.11 and 2.12. So, yeah, we're almost at chapter 3. This is getting wild. And then when we get to chapter 3, we're going to start learning how to count. Hey. All right. Stick around. I'm going to stop the stream, and I'll start it.